Okay, so let's look at a mathematical induction proof. So let's see. Let's prove the following: that f sub 1 squared plus f sub 2 squared plus f sub 3 squared plus dot 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 plus f sub n squared, let's prove that that is equal to f sub n times f sub n plus 1. Okay, so this function f represents the Fibonacci numbers. Okay, you may be familiar with the Fibonacci numbers. They go like this: 1, 1, 2, 3, 5, 8, 13, 21, and so on. Now, basically what Fibonacci says is that the first one plus the next one is equal to the sequential one. So any two added together equals the sequential Fibonacci number. 1 plus 1 equals 2, 2 plus 3 equals 5, 3 plus 5 equals 8. So the first one is obviously 1 squared. The second one is 1 squared. This third term is 2 squared. And then the next one in that sequence would be 3 squared. Alright, so this equation says that if you take all of those and add them up to any point that you decide to stop, square that, that's going to be equal to that one that you stopped at times the very next one. So all of those squared and added up equal is the same thing as this one times the next one that we didn't add up. Alright, so prove that. We're going to prove that by induction. Mathematical induction. Alright, also called induction 1. Now, with mathematical induction, we need a base case. Let's call our base case n equals 1. So then we're just going to plug in n into this stuff and see if it works. So if we, on the left side, if we say f to the 1 squared and we stop in at n equals to f sub n, which is 1, times f sub n plus 1. So times that one, or that one times the next one. Alright, so we know from earlier that the first Fibonacci number is 1, so that's 1 squared. The first Fibonacci number is 1, and the second number is also 1. So that's 1 equals 1, so true. Now we can state that the base case holds. Fact. Alright, so the second part of mathematical induction is assumption. Now for this assumption, just bear with me, we're going to take k, the letter k, and plug it in here for n. Alright, so we're going to say that f sub 1 squared plus f sub 2 squared plus f sub 3 squared plus dot 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 plus all the way to k squared, we're going to say that's equal to f sub k times f sub k plus 1. Okay, so the same as our first equation, just with k's in there. And we're going to say check. That's our assumption, or our hypothesis. And just we're going to accept that as fact at this point. And so I'll ask you to just take a look at that and just remember that. Alright, so the next thing with mathematical induction, obviously the first case is base, the second case is assumption, the third case is see if we can get from the assumed case to the next one by mathematical acrobatics, basically. Just algebraically, can we manipulate one to the other? And if we can, we've shown that one is true, and then we've shown that when any one is true, the next one is also true. Then by mathematical induction, we've proved the original case. So let's take a look at the next one after, in order after this case. So in that situation, we would have f1 squared plus f2 squared plus f3 squared plus dot 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 plus fk squared plus fk plus 1 squared. Okay, and what is that equal to? That's equal to the one you stopped at, fk plus 1, times the next one, which in this case would be f to the k plus 1, or plus 2. Alright? So that's equal to f to the k plus 1 times f to the k plus 2. So wherever k is, we go one more and multiply it times even one more than that, and that's equal to this, is what our first equation said. Is it true? Well, that's what we're working on. Okay, so this part here that we took special notice of, well, it just so happens that that is the same thing as this part, and this is equal to that, so we can take this part and plug that in here. Okay, so now we have f sub k times fk plus 1, and so that's the quantity that comes down from here. Those are equal based on our assumption. We've just made that fact in our mind. Now, this one we don't know yet, so is that true? Is that true? We've assumed this one to be true, and we're going to see if this one is true. Okay, so I've substituted that in here. Now what's left on the left side? Add fk plus 1 quantity squared. And is that or is that not equal to this stuff? Alright, well, if I just start my mathematical manipulation here, I can go ahead and check to see if I factor out an fk plus 1, what's that going to leave me? F sub k plus 1 factored out of this side, what's left? Well, if I factor this out of here, that leaves f sub k, and if I factor one of those, this is squared, so if I factor one out, I'll have one left, so fk plus 1. So yeah, distribute that back in, it would give me this, distribute it here, it would give me that. Okay, check. Now, is that equal to f to the k plus 1 times f to the k plus 2? Okay, well, if we think back to the definition of the Fibonacci numbers, any 1 plus the next one gives us the sequential one. So if we take any 1 plus the next one, it gives us the sequential one. So we know that this and this stuff is the same. So we can say now fk plus 1 times, these two are the same, so I'll go ahead and write them as the same. Fk plus 2 equals fk plus 1 times fk plus 2, and obviously these terms are the same and these two terms are the same, so check, that holds. And if we assume one to be true and then show that anytime one is true, the next one is true, by mathematical induction, we have proven our initial case. Thanks for watching.